Welcome everybody on our seminar of Quantum Information and Quantum Computing Group. Today our guest is Katarzyna Siudzińska from University of Nicolae Copernicus in Toruń, and the title of her talk is All Classes of Informationally Complete Symmetric Measurements in Finite Dimensions. Kasiu, please start.
Okay, thank you very much for introduction. Today, I would like to tell you a bit about types of measurements. So measurement operators, POVMs, specifically their symmetries and some applications. So I'll start with a quick reminder of what are quantum measurements and the two most popular classes, which are SIG POVMs and MUBs. In the main part, I will analyze the most general class of measurements with high symmetries, starting with a definition that is that can be viewed as a common generalization of both symmetric informationally complete POVMs and mutually unbiased bases. So this will be two special classes of this wider construction. Then I will focus on the characterization of sets of measurements that are informationally complete. I'll show you how to construct any such measurement with some examples of measurements that are neither in the class of SIG POVMs nor mutually unbiased bases. At the end, I'll show some simple applications, mostly in calculating entropy uncertainty relations and also applications in detecting quantum entanglement. And at the very end, I'll quickly summarize the most important results and list open problems if you'd be interested in pursuing this topic. So first, a quick reminder, measurement operators in quantum mechanics are characterized via such operators that are positive and they all sum up to the identity operator. And these are called POVMs, positive operator valued measures. Among these objects, there is an important subclass of POVMs that are informationally complete, often abbreviated to IC. This means that we have at least d squared of these operators, and if we take all operators E alpha, when n is equal to d squared, this is an operator basis. If n is greater than d squared, we'll have some linear dependence, but as long as these can be used to span the whole space of operators, then we'll still have informationally complete sets. Then among informationally complete POVMs, when well, we can we can characterize symmetric informationally complete POVMs. So now we impose some very strict symmetries to our operators. So first, SIG POVMs are such operators that we take d squared elements. Each E alpha is a rescaled rank 1 projector, and so the trace of E alpha is just 1 over d. And then we say that if we take two different operators P alpha and calculate the trace, then it has to be 1 over d plus 1. So it's a constant independent on the indices alpha and beta as long as they're different. Another class is mutually unbiased bases. So now we take rank 1 projectors onto operator bases in the Hilbert space. So this pk alpha is kth vector of alpha bases. And if we take the trace of projectors from the same basis, then we get a Kronecker delta. So this is orthonormal. And if we take one object from one basis and another from a different basis, then this trace has to be 1/d. So again, a very strict symmetry condition. Both of these objects, so symmetric informationally complete POVMs and mutually unbiased bases, have been generalized. So if we take SIG POVMs and now we drop the requirement that they are rescaled rank 1 projectors. So now trace of E alpha squared doesn't have to be 1/d squared, but we have some factor A that has to belong to a certain range so that E alpha is a POVM. Because of this factor A, now if we take a trace of two different objects, then we get another value on the right-hand side that depends on this coefficient A, but it's still constant, independent on alpha and beta. And these objects are called general SIG POVMs. Now, if we generalize mutually unbiased bases to mutually unbiased measurements, so again, E alpha k don't have to be rank 1 anymore. So trace E alpha k squared is some kappa, again, from a specific range. And the trace of elements inside one measurement, it's no longer 0, but equal to some other constant. And again, a trace of elements from different sets is equal to 1/d. So that's the general idea behind this generalization. However, these are not
So Kasia, can I ask a question?
Yes, of course.
Yeah. So I wonder, because I know, let's say, motivation beyond standard MUBs and SIGs, like from let's say from tomography or from foundations of quantum mechanics. So there are many classes of measurements one can consider. Okay, those classes are mathematically well defined, so I guess you, like, want to keep like overlap between them, like like constant in a sense, right? But like why to consider this, let's say, among outside of mathematics?
Okay, so first of all, maybe I should start with that. SIG POVMs and mutually unbiased bases aren't defined in any finite dimension. And these two objects are, of course, dependent on the coefficients A and kappa, but we can find such
You mean that you can find them?
Yes. So
Okay.
at least in these dimensions, they can be used, and SIG POVMs and mutually unbiased bases cannot.
Mm-hmm.
And also, in these areas that you mentioned, you can replace using SIG POVMs and MUBs with these objects. Of course, the results will be different, but sometimes it is more beneficial to use these generalizations.
Okay. So basically, the existence is the. I mean, okay, like it's a relaxation of definitions, but you can always, like in any dimension, you can find
Yes.
like examples. Okay, thanks.
I'll also mention these applications at the end, so maybe this will make things more clear for you.
No, everything is clear. Just yeah. Thank
Okay.
you.
So now we want to move a step further and ask, can there be a common generalization of SIG POVMs and mutually unbiased bases? And to answer that, let us take a set of n POVMs, where n can be fixed, of course, and each of these POVMs has m elements. And then we'll want to apply symmetry conditions that are similar to those satisfied by SIG POVMs and MUBs and see what happens. I call these objects N POVMs because they depend on these two constants. An NM POVM is a set of N POVMs. So a single POVM is characterized by the index alpha, and the elements inside a POVM are characterized by k. And k changes from 1 to the constant m. And now we impose the following conditions. So we want the trace of each object to be the same, independent on the indices alpha k. Analogically, the trace of a squared operator also is some constant. The trace of operators inside the same POVM is another constant. And finally, if we take one operator from one POVM, another from a different POVM, this also has to be constant. So this is all that is assumed at this point. So we have 4 constants that characterize this symmetric measurement. And now, from the properties of POVMs, these constants can be calculated. So W is related to the dimension of the Hilbert space and the number of elements inside a POVM. Y also depends on this constant X. This will be a characterizing constant of a symmetric measurement, so this stays. Similarly, like A and kappa were for general SIG POVMs and MUMs. This constant Z depends on the dimension and squared number of elements. And finally, for these operators to be positive, this coefficient X has to belong to a certain range. And what is important, on the right-hand side, we can get 2 different values depending on the value of D and M. Because it's a minimum, sometimes we get D squared over M squared, sometimes D over M. And what is now what we can infer from that? If X is equal to D squared over M squared, so this is just W squared, therefore such measurements would be projective measurements. On the other hand side, if X would be equal to D over M squared, it cannot be, but this explains why it is a sharp inequality. In this case, we get only E alpha k equal to identity operator. So it's not interesting for us. Therefore, this is dropped. Because only D squared over M squared corresponds to projective measurements, so all operators are rank 1 projectors rescaled, then we can see that if this minimum isn't D squared over M squared, but D over M, then we cannot have any projective measurements. So that is the result of this remark. Now,
I'm sorry, can I ask one thing? Maybe I missed it. Can you move back? So this this inequality X greater than D over M squared. So you exclude it because then it corresponds just to identities.
yes.
And you want to have non-trivial measurements. Fine,
Yes.
thanks.
Okay, so this was the most general consideration. Now we'll focus on informationally complete measurements. So we would like to have some constraints on these 2 numbers, N and M. Because if we take a collection, oh, sorry, this k should be in the lower index. If we take a collection of E alpha k, then they form an informationally complete set if we take minus 1 elements from each POVM, well, m POVMs would sum up to the identity operator. So let's get rid of the identity. The rest is m minus 1. We multiply it by the number of collections, and this has to be equal to d squared minus 1. So all the number of all operators in the operator basis minus the identity operator. So this is the constraint for informational completeness. We'll explore it in a moment. I would also like to use this property of informational completeness to show that if we take any quantum state rho, we can decompose it using probabilities P alpha k, which is just trace of the state with a measurement operator, and these operators F alpha k depend on operators E alpha k and on the identity operator. Now, going back to this equality, we can also observe some more properties. So if we take any finite dimension D, we can construct at least 4 informationally complete symmetric measurements. Because the choice of m and n that always satisfy this equality are as follows. So we can take m equal to d squared and n equal to 1. So this would correspond to general SIG POVMs. If m is equal to d and n is equal to d plus 1, then we have mutually unbiased measurements. And we have 2 more classes. So m can be equal to 2, n can be equal to d squared minus 1. And the final class, m is equal to d plus 2, n is equal to d minus 1. I now realize that I probably should include this equality also here, but you can check for numbers 1 to 4 that n times m minus 1 is always d squared minus 1 for these 4 classes. So we didn't make any assumptions on d, therefore this always works. But of course, if there are some specific dimensions d, then we can have even more. So the first non-trivial example would be in d equal to 5, when we can construct 2 more classes. So we can take n equal to 8, m equal to 4, or n equal to 3, m equal to 9. Again, this satisfies the equality for informational completeness. However, we can check that these choices of n and m do not fall into any of these 4 categories. Okay, so there are some mathematical formulas for measurement operators, but how to actually construct them? It turns out that all we need are orthonormal Hermitian operator bases, where one element is a rescaled identity and all the other elements are traceless. Using these operators G, we can construct operators H alpha K in a specific way that guarantees that this construction with equation 14 indeed gives us the symmetric measurements. Here is a constant number t, which can be found from the condition that E alpha k has to be positive. Then the positivity of the right-hand side of equation 14 can be translated into the value of the parameter t, where this lambda max, lambda min are maximal and minimal eigenvalues of operators H alpha k. And this construction, of course, works in any dimension. There is a simple relation between the coefficient x that characterizes symmetric measurements and this new coefficient t. The relation is with t squared, so you can see that for each x we can find 2 t's that correspond to it. Now, if we prove that all E alpha k are positive for a certain choice of x, then these operators would be also positive for any x prime that is smaller than x, but still has to be greater than d over m squared to exclude identities. So the trivial case. Depending on the choice of operators g alpha k, there exists an optimal value of this parameter x that, let me just call it x opt from optimal. And this optimal value, if it reaches the upper bound of x, then the corresponding symmetric measurement is called optimal. So among these optimal measurements, we have, among others, SIG POVMs and mutually unbiased bases. Because the relation between the measurement operators E alpha k and the Hermitian basis is 1-to-1, we can always find the corresponding operator basis for a given measurement. And this G alpha k depend only on the elements of the measurement and identity operator. What is important, any informationally complete NM-POVM can be obtained using this construction with Hermitian operator basis.
I'm sorry, can I ask about the last remark? So, like, because if I understood, I don't remember the parameters really, but like for probably n equal to 1 and no, from probably m equal to 1, that corresponds to SIG, right?
Yes.
So, and problem of finding, I mean, okay, today there is a very nice paper on Archive that claims to solve the SIG problem, but aside from this, it's like, you know, like unclear whether SIG exists. So this, you will not recover, like, can you recover SIG by finding suitable basis of operators?
Yes, but choosing this basis isn't as intuitional as you'd think. Because I tried this taking SIG for d equal to 2, 3, 4, and I didn't see any simple relation between the Hermitian operator basis that I recovered from them to then generalize it to any d.
I see.
But give me a SIG POVM, I'll find you a basis that can be used to construct it.
Okay. I see. Yeah, but this is like some very specific property of this operator basis, let's say. Sure. Okay.
Yes, the problem is existence. So there exists such Hermitian operator basis that corresponds to a SIG POVM if it exists, but then if I don't know the form of the SIG POVM, I'll just pick at random.
Okay, thank you.
Okay, we can find an intrinsic relation between two families of symmetric measurements. If we take one NM-POVM that is characterized by numbers n and m, we can find an object that I called dual to it, and it characterized by n prime, m prime, which are corresponding to these numbers n and m in this following way. The interesting thing about these two POVMs is that they are both constructed from the same orthonormal basis, but we just swap the indices. So if for the first symmetric measurements we had K numbering elements, alpha numbering POVMs, then for this dual POVM, we have the opposite. Some examples for SIG POVMs would be, so we have n equal to 1, m equal to d squared. So now we find n prime and m prime. So this is one of the two other classes among these 4 classes of measurements that can be constructed in any dimension. So now we have d squared minus 1 for the number of POVMs, and each of them is 2 elemental. And on the other hand, for mutually unbiased basis, where we have n equal to d plus 1, m equal to d, dual would be the 4th family, where we have d minus 1 families of symmetric measurements, and each of them has d plus 2 elements. Now let me show you an example of symmetric measurements that are neither SIG POVMs nor mutually unbiased basis. So we take n equal to d squared minus 1 and m equal to 2. Now, from the construction, it can be shown that the elements of this family of measurements is just well, the right-hand side, where G alpha are our Hermitian operator basis elements. The upper bound for x in this case, for the specific choice of n and m, is d over 2, and this corresponds to the following choice of the parameter t. So it is plus minus this right-hand side. It also can be rewritten in terms of eigenvalues of the operators H alpha k. And from this, we can see that the extremal eigenvalue of G alpha, so the minimal and maximal, would be either of this. So we have 1 over square root of d, and therefore, we can now move to a more specific case, because, well, for a general case, what Hermitian operator basis do I choose so that this is satisfied? Well, I wasn't sure, but if I take d equal to 4, then it becomes obvious. So for the operator basis, let us take a tensor product of normalized Pauli matrices. So we have sigma 0 equal to rescaled identity, and then sigma 1, sigma 2, sigma 3. Now, the corresponding symmetric measurements are defined via this simple formula, and it turns out that all of these elements are rank 2 projectors. So because I took, for this example, the only general case where rank 1 projectors cannot be reproduced, it turned out that, well, we still have projectors in this optimal case, but now they are rank 2, not rank 1. Okay, so these are all mathematical considerations concerning measurement operators, but what about the applications? So the general assumption is that the applications for symmetric measurements would be similar to those of SIG POVMs and MUBs. So let me show you, or list actually, what are common applications of these two families of measurements. So in quantum tomography, we use them for quantum state estimation. Both SIG POVMs and MUBs are shown to be quantum 2 designs. So wherever designs are used, we can also apply those. in post-processing tasks. Then in quantum cryptography, we use SIG POVMs and MUBs for quantum key distribution protocols. In quantum entanglement, they are used to characterize sufficient separability criteria for quantum states and also to construct entanglement witnesses, specifically band entanglement can be found using these witnesses. Then in foundations of quantum physics, we use SIG POVMs and MUBs to construct entropic uncertainty relations. And also there are many papers that analyze mathematical similarities between these two families of measurements. So,
sorry, Kasia, can I ask
yes.
what you mean by post-processing tasks?
Any tasks that are carried over after transferring quantum information. So,
but do you mean things like shadow tomography, or like the fact that they are informationally complete and therefore you can do some tricks?
Okay,
like
shadow
this?
tomography would be one example. Sure, there was some generalization of shadow tomography where this could also be used, but now I don't remember the name. So,
No,
okay.
I'm just like, always genuinely interested in all applications of POVMs, and this I just didn't know. That's why I'm asking.
Okay, so you know what? I don't remember more post-processing tasks on the spot, but I'm sure I have it listed somewhere when I was researching this, so I could send you the list maybe later.
Would be great. Thank you.
In the last part of the presentation, we'll focus on these two applications. So in quantum entanglement and in entropic uncertainty relations. So for uncertainty relations, let me recall that we can construct an object called index of coincidence that is a sum of squared probabilities. So we take the measurement elements E alpha k, trace them with the state rho, and sum of these operators squared is the index of coincidence. For informationally complete symmetric measurements, it can be shown that for any state rho, the index of coincidence is upper bounded by C tilde, which is dependent on the dimension of the Hilbert space of the number of elements M and on the coefficient X that characterizes the measurements. N doesn't appear anywhere because for informationally complete symmetric measurements, it is dependent on D and M, so that's why it canceled out. Now, using this index of coincidence, we can characterize uncertainty relations for the Shannon entropy. So with each measurement E alpha, we associate the Shannon entropy where P alpha k is trace of rho with E alpha k. And if we average over this Shannon entropy on the left-hand side, 1 over n because we have n families of measurements, then this is lower bounded by a logarithm of n over c, where c is the index of coincidence. If we take only optimal measurements, it turns out that this right-hand side is the smallest if we take n equal to d squared minus 1 and m equal to 2. And the largest if we stick to symmetric informationally complete POVMs. You know what, one moment, it became very dark in my place. Let me just switch on the light. Much better. Now, moving on to applications in entanglement detection. So first, let us focus on separability criteria. We take a Hilbert space that is a product space of HA and HB, where dimensions of each space are simply dA and dB, and on each Hilbert space we define symmetric measurements. Well, again, these can be different and labeled by A and B respectively. Linear correlations between these two families of measurements are encoded in the correlation matrix, which depends on 4 indices. And on the right-hand side, we take a tensor product of 2 elements from each symmetric measurement. So now, if the mixed state rho, a bipartite state, is separable, then a trace norm of the correlation matrix will be upper bounded by a square root of C tilde alpha C tilde B, A and B, where C tilde is the upper bound of the index of coincidence and A and B labels measurements. If we take both measurements to be SIG POVMs, then this inequality will recover the ESIG criterion from the following paper. Now, in a simpler case, when the dimensions of Hilbert spaces HA and HB are the same, and the symmetric measurement operators are also the same on both spaces, we can show that if rho is a bipartite separable state, then trace of the correlation matrix is upper bounded by the maximal value of index of coincidence. And here is no need to distinguish between CA and CB, because operators from the subspace A and B are the same, so the C tilde will be the same for A and B. Another approach to detect quantum entangled states is to construct entanglement witnesses from symmetric measurements. So we take not necessarily informationally complete NM-POVMs and define trace-preserving maps phi alpha, where this OKL alpha, these are matrix elements of orthogonal rotations that preserve the maximally mixed states N ast. Using trace-preserving maps phi alpha, we now construct a linear map phi, where these coefficients A and B depend on the number L of maps phi alpha that come into this phi with minus, on the total number of measurements, and also B depends on X minus Y. This is the coefficient that characterizes symmetric measurements, and Y also characterizes symmetric measurements. It was the trace of 2 different operators from the same POVM. So all of these constants are known. And a map phi constructed in this way, regardless of the number L, is always positive and trace preserving. Therefore, we can use it to construct entanglement witnesses. So via the Choi-Jamiałkowski isomorphism, we calculate W, where these operators, well, these objects H alpha depend on POVM elements E alpha K. This bar is complex conjugate, and also on the rotation matrix. Because there is a one-to-one correspondence between the measurement operators E alpha K and Hermitian orthonormal basis, we can find another form of this entanglement witness W that uses only operator basis. So after rewriting it using G alpha K, we have the following form where this Q mu nu are matrix elements of Q, which is a block diagonal matrix. And this Q1 to Qn, the form of this can be easily found, but it's relatively complex, so I thought it wasn't important to list it here. The important thing is that this Q is block diagonal, and therefore entanglement witnesses constructed from symmetric measurements fall into the witnesses from the CCNR criterion. In general, from this criterion, we obtain entanglement witnesses with any matrix Q and any operator basis G. Here, what changes is Q is diagonal and G are traceless plus the identity operator. So what I would like you to remember from this presentation is as follows. There is a general class of symmetric measurements that includes both symmetric informationally complete POVMs and mutually unbiased bases. It also includes two additional classes of informationally complete measurements that exist in any dimension. For specific dimensions, there can be even more classes. Also, to obtain symmetric measurements, all we have to do is choose Hermitian orthonormal basis with identity and traceless elements, and in this way we'll obtain any informationally complete symmetric measurement. Important open questions is, well, first, finding more optimal NM-POVMs in finite dimensions. The downside is that this open problem includes finding SIG POVMs in any dimension and also finding mutually unbiased bases in composite dimensions. So these are two not easy problems. On the upper side, we have more classes of measurements that fall into this category, and they haven't been analyzed as thoroughly as SIG POVMs and MUBs. So there could be some room for improvement. The other thing is comparing the applicational efficiency of symmetric measurements with what is already known for both SIG POVMs and MUBs. Here, I would also like you to know about further research that has already been done for symmetric measurements. So examples include finding sufficient conditions for the existence of optimal NM-POVMs. So this is partial answer to the first open problem. Improved separability criteria, even compared to those that I listed here, have been found. They have been used to construct entanglement witnesses that detect band entanglement, so indecomposable entanglement witnesses. They have been used in steerability, and entanglement detection. Also, further improved entropic uncertainty relations have been found, and uncertainty relations for other entropies, not only the Shannon entropy. Symmetric measurements have been used to characterize average coherences, Bruckner-Zeilinger invariants. They were also applied in key distribution protocols, and it has been shown that symmetric measurements form conical 2 designs. So in this case, they are also similar to SIG POVMs and MUBs, which were known to form conical 2 designs. And because 2 designs are used in optimal state estimation, therefore symmetric measurements can be also used here. And finally, symmetric measurements were applied to construct dynamical maps for open quantum systems, and they have been characterized in terms of Markovian and non-Markovian quantum evolution. So as you can see, there are already quite a lot of topics covered. However, well, there is still a lot of things to check. Especially that later I introduced 2 generalizations of the objects that I showed you today. First is taking n POVMs, but allowing for each POVM to have a different number of elements. So here we had a constant number of elements m. Now we take number of elements m alpha, so it depends on the choice of POVM, but there are still n of them. So that is one generalization. Another generalization is introducing informationally overcomplete measurements. So now we distinguish between informationally complete, so they are exactly these squared minus 1 elements different from the identity that are linearly independent. If we move to informationally overcomplete, now we have some redundancy, so even more operators introduced here. If you'd be interested, I can also tell you about these 2 generalizations. For today, I thought it would be too mathematically complex to start from either one of those. The entire presentation was based on 4 of my publications. So symmetric measurements were introduced in paper number 1. In 2, I constructed entanglement witnesses from these measurement operators, and 3 and 4 consider their generalizations. So if any of you is interested, I'd be honored if you check this out. And of course, if there are still questions to what I showed you, please ask them. And thank you for listening.
Kasia, thank you very much for a very interesting seminar. We are going to consider your suggestion to continue these subjects you've just mentioned. Are there any questions? Maybe I have one. If you can get back to slide number 7, then there was a simple condition for existence, not 7, 6 in that case. Yes, this equation number 10. So as far as I understand, please correct me, this equation defines the condition for existence of NM POVM. Is that correct?
Of informationally complete NM POVM.
Informationally complete. So this is just a matter, so instead of how to phrase my question. So this is actually a question about factorization of the right-hand side. So if we can just decompose this square minus 1 onto 2 factors, then we can state the existence of such an object. Yes, that is correct.
Yes, that's exactly correct.
Okay. Let me check my notes. what I wanted to infer from this. Okay, so I think this is what I wanted to know. One more question is, maybe this is a very stupid question, but I have to ask it. For mutually unbiased bases, there is a problem that actually they exist in any dimension, but the problem is with a complete set of mutually unbiased bases. This we don't know whether they exist, especially for composite dimensions. But there are papers by Siudziński and Hismayer in which they proved that if we have an extendable mutually unbiased basis, then it can be used in a very efficient way to detect entanglement. This is what you partially mentioned in your presentation. But what about in your case, in NM POVMs? Can it also be used to detect entanglement when you consider incomplete set of these operators? Is it as efficient as in the mutually unbiased case?
I didn't check efficiency. All I did was finding examples of indecomposable entanglement witnesses that cannot be constructed using mutually unbiased bases, and also incomplete sets of these symmetric measurements. So that is all. I don't know about anything else. So how would you check efficiency in detecting entanglement?
But I just said that this is much more efficient because this is what is said in the paper of Siudziński. They claim that when you have an extendable mutually unbiased basis set, then you can efficiently detect entanglement. This is what I mean actually, what I've just said.
Okay. I would have to check this paper. And then maybe come back to you, because I would have to check this definition of efficiency and if it can be applied also in this case.
I put on the chat the paper that I was just going through. This is a well-known paper by Beatrix and Darek and Daniel McNulty also. We know these guys. Okay, are there any questions or remarks? Cannot see. Okay, Kasiu, thank you very much for a very nice presentation.